our proving trig identities are going to be really similar to what we've been doing with the simplifying trig identities. The only difference is now instead of just like starting with something and then just going until you kind of think that you should stop, now we have an end that it tells us that, okay, you have to make this side equal this other side. So we know what the end is going to be or what we're trying to simplify it to. But we're still using the same identities and a lot of the same steps. So here are just some guidelines. You don't have to have all of these like memorized or write down or anything like that. It's just kind of like some things, different techniques that we're going to be going over. Now, the one that you really do have to remember or know is this first one, and that is we want to start with the most complicated side. So that is something that you have to remember. Other than that, basically it's going to depend upon the type of problem that it is. So sometimes we're going to convert everything to sines and cosines. Sometimes, especially when we have squared things, we might use our Pythagorean identities. We can also just do some like basic operations, so like factoring, multiplying, adding or subtracting. Sometimes we'll have to multiply by a strategic one. Sometimes we'll have to factor out the rabbit, which we'll be looking at that in our next set of notes, kind of like what that means. And then the last thing is just let's try something. The worst thing you can do is just like stare blankly at the piece of paper and wait for it to like speak to you and tell you what to do. Because sometimes even if you do the wrong thing, well then that lets you know, okay, well that's not an option. Or sometimes like as you do some different steps, you go, oh, okay, I know I can use this now instead. The more that you practice these types of problems, the better that you kind of get at knowing which technique to use when. But you do have to practice. And as long as you start somewhere, usually you can eventually get there. So let's look at an example. So it says to verify the identity. Proving and verifying mean the same thing. So you'll see both in the directions. It says prove the identity or verify the identity. It just means that we're going to start with one side. We're going to do some steps. And we need to end up with the other side. Now, do realize that this is an identity. It's not an equation. So I can't like add or subtract things to both sides. I can only start with one side, use my other identities, and simplify things to try and end up with the other side. Which is why we want to start with the more complicated side, because usually it's easier to like combine things or rewrite things than it is to try and like start with something that's really simple and break that apart. So in this case, which side do we think is the more complicated side?
The left side.
Yeah, so our left side has a fraction and it has like multiple things in there. So usually that would be where we're going to start. So we have secant squared of theta minus 1 divided by secant squared of theta. So what do we notice? Numerator is one of the higher differences. Agreed. I noticed that we have a secant squared on top and bottom. Can we reduce those secants? Why not? Because of the minus 1 of the numerator. Agreed. So be careful with that, because a lot of people, that's their first instinct, is they see something that looks like this, and they just want to reduce the things that are the same, right? But yes, because we have that subtraction of the minus 1, we can't reduce our secants or our x's with the limit item. But yes, our secant squared of theta minus 1 is squared and has a 1, so it looks very similar to one of our Pythagorean identities. Now, is it one of my Pythagorean identities? Like just as it is? Not quite, right? So I have a secant squared and we have a 1. So notice on my second Pythagorean identity, if we subtracted 1 from both sides, we end up with secant squared of theta minus 1, which is what we have. And so we know that that's just going to give us tangent squared of theta. So remember, sometimes we will have to rewrite or kind of move stuff around on our different identities to be able to get to what we have here. Alright, so now we have tangent squared of theta divided by secant squared of theta. Are we done? Can we stop there? How do we know we're not done? Yeah, so that's what's nice about these is that like we know when we're done now when we get to what it has to be. Whereas before we just kind of had to be like, oh yeah, that looks kind of simplified. Versus now we actually have an endpoint in mind. So what might we want to try now?
Make everything sine or cosine.
Agreed. So a good kind of hint is that if my answer just has sines or cosines in it, and right now my stuff doesn't have sines and cosines in it, usually it's a good idea to then convert everything to sines and cosines. So what does tangent squared of theta equal?
Sine squared theta over sine squared theta.
Agreed. And then what does secant squared of theta equal?
1 over 2.
Agreed. So notice that we have a fraction within a fraction. So what do we do?
I know you have like a term for it, because Haley told me about that, but I don't remember you telling us about that. But you take the bottom fraction, flip it, and multiply it.
So I multiply by the reciprocal?
Yeah.
Or we keep it, change it, and then flip it. So now, what's nice? What happens? My cosine squared reduce, but yes. And then what are we left with?
Sine squared theta.
Which is what we want, yes? Agreed?
Yes.
Now, could there have been another way to do this instead? Maybe?
Well, I'm sticking to lots of things.
This is true. There's always more than one way. And as long as you're using your trig identities correctly, it doesn't matter which way you use. The other thing that we can notice is we can't reduce our secant squares, but because we just have secant squared in our denominator, notice that we could have started by breaking this apart into two fractions instead, which is okay as long as we divide both of them by that secant squared. Yeah. And then what is secant squared divided by secant squared? 1. And then what is 1 divided by secant squared? Cosine squared. And then kind of like we talked about in our other one, well, this isn't one of my Pythagorean identities, but it looks very similar to one of my Pythagorean identities. So notice that on my first one, if I subtract, right, my cosine squared over, I would get sine squared equals 1 minus cosine squared. So I know that 1 minus cosine squared equals then just sine squared theta. So now the only difference between these two, they have about the same amount of steps. The only difference is like on my first one, I ended up with a fraction within a fraction. So like if we got to that step and it looked super confusing and we didn't know what to do from there, we might try a different approach. Does that make sense? So there's usually more than one way that we can get to something. It just depends on which way you see and which type of technique that you feel the most comfortable with. I'll say for the most part, most students don't struggle with the like trig stuff, right? It's pretty easy to substitute 1 divided by like secant squared for cosine and those types of things. What you'll usually struggle with are the algebra stuff. So like simplifying complex fractions, adding and subtracting fractions, all of those things. So just be careful with your steps. So then, the last thing that we have to do, once we get what we wanted to get, so our right-hand side in this case, we need to write a conclusion statement, which looks something like this. So we're going to say, therefore, so the 3 dots in the triangle mean therefore, and I'm basically going to state the statement that I was trying to prove. So we showed that we started with the left side, and we did some steps, and we were able to get that to the right side. So we showed that those two things are equal. And then the last thing that you do is you draw a little box. So basically the box means I've done the end, the proof is finished. Okay? You don't have to use the 3 dots, like you could actually write out the word therefore, but you do need to put something, or you can put then, or so, or something like that, but you need to put a conclusion statement that tells me that you know that you finished and you showed what you were supposed to be showing. You all with me on that? Okay. So let's look at another one. So in this one, I have 1 divided by 1 minus sine of alpha. So that is in alpha. Just like we use thetas and pi's for things, those are both Greek letters. Alphas and betas, and sometimes gammas are also Greek letters that we'll see come up. And they're just another letter that we can use for a trig function. So if you haven't seen your Greek letters, you can familiarize yourself. Basically, it's all of those like fraternity and sorority letters and signs that you're used to seeing. Like all of those letters are Greek letters. In this case, we're using an alpha. So this time, what side might I start with? Left. Probably the left. My right side has a squared, which like my left side doesn't have. But kind of like I said at the beginning, here on the left side I have 2 fractions that I'm adding. Usually it's going to be easier to combine things together than it is going to be to try and like break things apart for my secant. So we'll go ahead and start with the left side. So we have 1 divided by 1 minus sine of alpha plus 1 divided by 1 plus sine of alpha. What do we want to do?
I want to say factor.
We can't factor it because we don't actually have anything that's the same for whole. Does that make sense?
Yeah, common denominators.
Correct. So we do have 2 fractions. We're adding those 2 fractions, so we can combine them to be 1 fraction as long as I have a common denominator. So what do we need to multiply our first fraction by? One plus 3. But we do need to do it to the top and the bottom. What about our second fraction? 1 minus 9. Yep. And again, I have to apply to the top and the bottom. And we do that because now notice on top I have 1 plus sine of alpha. So now that our denominators are the same, what are we allowed to do?
Multiply.
Not multiply, but just
Oh, yeah,
add them, combine them. Just be careful, because remember that when we add things that have a common denominator, that denominator does not change. Just like if I had 1/3 plus 1/3, I get 2/3. That 3 stays the same all the way across. I don't do anything to it. So I'm just going to rewrite that denominator. So then notice on top, if we simplify our addition, what are we going to end up with?
2.
Just 2, right? Because 1 plus 1 gives us 2. And then sine of alpha minus sine of alpha is 0. Well, that's helpful because if I notice on the right-hand side of my beginning statement, I have a 2 there. So we know we're a little bit closer. Okay? But right now we still have signs in our denominator. So what might we do? We can multiply it out. It's a binomial times a binomial. So we're going to have to multiply or FOIL it out. So I have 1 times 1 gives us 1. Then I have 1 times a negative sign.
Negative
It's going to
sign.
be negative sign. Then we have a positive sign times 1. And then I have sine of alpha times negative sine of alpha, which will give us what?
Negative sign.
Degree. And remember, whenever we're writing our squares for our trig functions, we put it on the inside, not after the angle. So now, what happens to our 2 middle terms? A positive sine of alpha and a negative sine of alpha, so they add to 0. So I'm just left with 1 minus sine squared of alpha. Well, what is 1 minus sine squared of alpha? So we have a squared there, which should probably tell me I'm probably going to use one of my Pythagorean identities. So notice if we subtract sine squared from both sides on our first one, then we get cosine squared of alpha equals 1 minus sine squared. So we know that this becomes 2 divided by cosine squared of alpha. And what is 1 divided by cosine squared of alpha? Secant squared of alpha, right? But here I've just multiplied by a 2, which means that I'll just multiply my secant squared by a 2 as well. So we end up with 2 secant squared of alpha, which is nice because that's what we want to do. So again, we know that we're done because we've gotten ourselves to the other side. So we can state our conclusion statement. So therefore, 1 divided by 1 minus sine of alpha plus 1 divided by 1 plus sine of alpha equals 2 secant squared of alpha. And I draw on the lid of the box to say that. Questions on that? Yeah? there's a lot of steps there, right? But none of them are risk to the car in and of themselves. You just kind of have to work your way through each one. Which is also why it's really important to make sure that you show each of your steps and that you write them out neatly. Because then that way, if you make a mistake somewhere, it's easier to go back and fix that. If you don't have to go all the way back to the beginning, you can just go to whichever step you need. Right, see, I think that is the last one.